Alright everyone, it's Mr. Edie back with yet another video. Today guys, we're going to be talking about our fourth topic in kinetics, which is on collision theory, okay? So let's just start off by keeping things simple, right? So in chemistry, the very core of it is when we have atoms and molecules collide, there could be one of two things that happen. One, there's no chemical reaction, or two, there is in fact a chemical reaction. And in terms of how I want you to picture how atoms and molecules collide, guys, the best way that I could bring this to you is looking at a lottery machine during a Powerball draw. So we're going to quickly just watch this little clip here. And as you guys can see, the lottery machine is first off starting to get these lottery balls happening with enough energy. So let's watch it again. So energy starting to be going up, and then obviously enough energy happens, and those particles, right, if we're relating them to chemistry, start to move much faster and faster. If they have enough energy, they will break old bonds and form new ones. And again, what I want you to picture is, again, this lottery machine, okay? So energy building up, and now we have a lot of energy in the system, and presumably if we have enough energy, we can break old bonds and form new ones. That, of course, would be a chemical reaction in and of itself, okay? So factors that would affect the rate of a chemical reaction are several things. First, it could be the temperature in which we're having the chemical reaction occur at. Okay, so temperature's one, concentration's another. So if we had a 6 molar solution versus a 3 molar solution versus a 1 molar solution, there would be an effect as we slowly diluted that concentration in terms of how fast the chemical reaction can actually occur. Another point would be introducing a catalyst. So catalysts will speed up the rate of a chemical reaction because they lower the energy of activation. Another point would be gas pressure, okay? And our last one would be the surface area of a solid reactant or the surface area of a catalyst would also all affect the general rate of our chemical reactions here, okay? Now, let's continue to the next slide. So in terms of discussing temperature and rate, what we want to look at is the collision model, okay? So the collision model assumes that the reactions occur as a result of collisions between molecules, like we just said on the previous slide, okay? This helps explains why the magnitude of rate constants increase as the temperature increases, okay? There's greater kinetic energy of the colliding molecules equals the greater energy of the actual collisions. Okay, so kinetic energy, of course, depends on temperature. Because remember, temperature is a measurement of how fast the particles are moving, how far, what they're looking like in terms of motion. So if that's what temperature is measuring, it measures the kinetic energy, then kinetic energy in of itself is dependent upon temperature, right? So we take a look at this Maxwell-Boltzmann distribution. So first things first here, guys, this distribution is specifically comparing temperature, okay? It's comparing the same reactant at two different temperatures. And what you're going to notice, at higher temperatures, there are simply more particles at a higher energy, which means the chemical reaction can occur faster. So this curve here saying, okay, yeah, there's more particles that have reached the point in which they can activate, right? They can undergo a chemical reaction. They have sufficient energy to break old bonds and form new ones. Since there's more of those particles at that energy state, the chemical reaction is simply going to happen faster when comparing it to the blue curve, right? That blue curve, there's less particles ready to actually react. Therefore, the reaction itself is going to occur slower, okay? We can look at this in the form of energy diagrams, and this isn't going to be the only unit where we see energy diagrams, nor is this going to be the only section in which we see them, everyone. We will see them again in Unit 6, but suffice to say, an energy diagram has 3 unique parts. The energy in which the reactants have, the energy of activation, which is how much energy is required for that chemical reaction to occur, and then finally the energy of the product. So what happens after the reaction is of course over. Now, in terms of the energy of activation, what does this really mean? So I want you guys to just simply think about the fact that if we had, a stick or your pencil in class, theoretically speaking, if you rub the stick together, right, or you try to do that spindle thing you see in Survivor shows, right, you could technically ignite the pencil or a stick to make a fire by friction set, right? Now, why is it, though, that it's so hard to create fire by friction? Well, what you're doing when you're spinning the stick very fast between your hands, right, in order to create a friction fire like that, you're actually getting the molecules or atoms of the wood up to the energy of activation in order for them to react with the oxygen in the air to create a fire. So if you hit that energy threshold, which is taking the reactants up to this energy state at the top of this hump here, okay, that's what we would call the transition state, only then can a chemical reaction occur, because the bonds that were originally in the reactants, in our case our stick, have now started to break. And now they can form new bonds with the other reactant, aka the oxygen, in our case here. And that minimum of energy to put into it is our EACT, or energy of activation. Okay, at the top of this is our transition state. As I said, that is where our reactants are breaking their old bonds and they're forming new bonds in order to form the products. Okay, so again, very unique parts in form of our energy diagram. The beginning part of the energy diagram, of course, is your reactants. The top of the hump where the EACT is, right, the energy of activation, that is our transition state. As I said, that's where old bonds are breaking and new bonds are forming. And then the products could either be at a higher state of energy than the reactants, or a lower state of energy, as in this case, than the reactants. Okay, we'll talk about exactly what delta H is in our next unit, but that's how we would read and interpret an energy diagram. Okay, now there are ways that we can lower the EACT. Okay, we can lower EACT by, as an example, having a catalyst. Other things we can do with energy diagrams is we could simply take our reactants and we can help them along by putting them in a higher state of energy to begin with, so they don't have as much energy to surmount the reaction barrier, i.e. achieve the transition state there. So ways we can increase the energy overall, the kinetic energy of the reactants, again, changing the temperature, changing the concentration, increasing surface area, would all be ways we could get our reactants closer to surmount that reaction barrier, i.e. achieve a transition state. Okay, now the Arrhenius equation is going to relate the rate constant K of our mechanisms and our chemical reactions, our reactions rates, etc., from the rate laws to the activation energy, EACT, and temperature. So it is the rate constant K is equal to capital A E to the negative EACT RT, where EACT is your activation energy in kilojoules per mole. Your temperature is in Kelvin. The R is your gas law constant, and it is 8.31 joules per mole per Kelvin. Okay, so you'll notice it's not the ideal gas law constant. It is simply the gas law constant. So it's a different number here. What's different about it, guys, is that this has energy units. Okay. And then A is called the frequency factor, which is related to the number of times the reactants approach the activation barrier per unit time. So capital A is how many times do our reactants, are they ready to react or are they not? And how many times do they approach that activation barrier per your unit time? Okay, so again, super important to note, guys, that the gas law constant here is not our typical one. Again, the key difference here, the way that we know it's just the regular R gas constant versus the ideal gas law constant, is the fact that this has an energy unit in the form of joules. But nonetheless, those are what these variables mean. Okay. Now, although for the AP exam itself, guys, you were not responsible for plugging in any calculations whatsoever into the Arrhenius equation, I think it's important to for you guys to see how this is actually used with numbers, because personally, just simply looking at it conceptually, you know, it's hard to make that connection. So let's run an example with it in which we use numbers, okay, to reaffirm what exactly we can use the Arrhenius equation for. So you'll notice here, guys, that I have the Arrhenius equation rewritten in two different manners. One where they are included the natural logs. I personally opt to use the second equation where it says the natural log of K1 divided by K2 is equal to the energy of activation divided by the gas law constant times 1 over the temperature for T2 minus 1 over the temperature of T1. So that's the Arrhenius equation I personally like to use, okay? And if we're taking a look at this example, it says the rate constant for the reaction below was determined at 2 temperatures. Okay, so it gave us chemical reaction, and it gave us the temperatures at 25 degrees and 45 degrees Celsius. Gave us the rate constant, but also gave us the natural log of K, gave us the temperature in Kelvin, and it gave us 1 over temperature. So it did a lot of the math for us here. We're really just going to have to plug in numbers. And it wants us to determine the value of the activation energy for this chemical reaction. So we want to find the E-act. Okay. So guys, before we go anywhere, I do want to point out something that's super important that the Arrhenius equation is supposed to do, right? It's supposed to show us how the magnitude and temperature will, excuse me, not the magnitude and temperature, but rather the magnitude of the rate constant changes with respect to temperature. So you'll notice the rate constant increased, right? It went from 4.2 times 10 to the negative fifth up to 6.2 times 10 to the negative fourth when we increase the temperature by 20 degrees Celsius. That is a substantial difference here. It's showing that the rate is increasing as temperature is increasing, as evident in the increase in the rate constant. So again, super important here that the rate itself is being directly affected because an increase in temperature increased the rate constant. So that's something that's very significant that we're going to touch upon more in class. But I'll say it again. The overall rate of this chemical reaction increased as we increased the temperature by 20 degrees, as evident in the magnitude increase in the rate constant. Again, the rate constant went from 4.2 times 10 to the negative fifth up to 6.2 times 10 to the negative fourth. So just keep that in mind. Now, guys, what we're going to do is actually solve this problem, which is determine the energy of activation for this chemical reaction. Okay, so in order to do so, we're going to take the natural log of K1 divided by K2, and we're going to set it equal to the energy of activation, E-act, divided by the gas law constant R, times 1 over T2 minus 1 over T1. Okay. Now, we could do several things at this point, folks. You could, as an example, take this and we could we could solve for E-act algebraically now, or we could plug in our numbers and reduce first, then solve. From the looks of it, guys, I think it's going to be easier to do the latter. So that's what I'm going to do is I'm going to plug in some numbers real quick, and then I'll be back and we'll walk through simplifying it together. Okay, guys, so as you can see, all I did so far was just plug in our numbers respectively for K1, R, and T1 and T2. So now I'm going to simplify our numbers here, okay? And I'll be back in 1 second. All right, so our first simplification is we get the natural log division would be negative 2.692, and that's going to equal to, I move the number you get when you subtract the temperature, 1 over the temperatures to the top of the numerator here, and then of course I have joules at the bottom. To clear our fraction here, right, I'm going to have to multiply by the reciprocal on both sides, so it's going to be 8.31 divided by 2.11 times 10 to the negative 4 on both sides. This side, of course, it will cancel, so cancel here, cancel there, and we're going to be left with E-act is equal to negative 6.92 times, excuse me, don't forget this negative here, Mr. Reedy, 8.31 over negative 2.11 times 10 to the negative 4th. So I'll be right back. And we get the E-act to be 1. So we get 100,000, 10,000 joules per mole per K, or 110 kilojoules per mole per Kelvin. And that would be the E-act for this chemical equation. Okay, so again, that's what the Arrhenius equation is used for. It's to relate the rate constant with respect to temperature to the energy of activation. Okay, guys. With that being said, let's continue on now to our next topic. So, continuing with the Arrhenius equation, we already know what the rate constant is equal to. The exponential factor is the number E to the E-act divided by RT. And this represents a number between 0 and 1 that is a fraction of the molecules that have made it over the reaction barrier. Okay, so that's what the exponential factor is how many actual molecules have enough energy to surmount the reaction barrier. Now, this increases, or as you are closer to 1, as the temperature increases. So as we increase temperature, guys, we're going to increase the number of molecules that have enough energy to surmount the reaction barrier, okay? And again, that's what number E raised to the E-act divided RT is talking about. This decreases, or will become closer to 0, as the activation energy increases, okay? So if we have very high activation energy, that means our exponential factor is going to be very small. Conversely, if we have very high temperature, it will be very low, okay? Now we have to talk about orientation. So again, with the Arrhenius factor in mind, A is that frequency factor, which is talking about the number of collisions and ultimately their effectiveness of being favorably oriented. So therefore, we can rewrite this as the rate constant is equal to PZ raised to the E-act divided by RT, where P is the orientation factor and C is the collision frequency. Suffice just to say, the orientation factor is talking about, guys, if when the molecules collide, are they colliding in a manner, okay, that favors a chemical reaction. So not only in order for a chemical reaction to occur, do you must have sufficient activation energy to surmount the barrier, but Oh, excuse me, let me restate that. Not only must you have sufficient energy to surmount the reaction barrier, but you also must collide in a way that the orientation would be, quote, a successful collision. Sometimes if a molecule collides in one way, no chemical reaction will happen, even if there's sufficient energy. Okay, so again, you have to have you have to have the correct orientation when those molecules collide, in addition to having the sufficient energy for reactions to occur. How do we look at this? It's through the orientation factor. Okay, so more things about the orientation factor. As I said, it's a number between 0 and 1 that represents the fraction of collisions with an orientation that allows for a chemical reaction to occur. Okay, the closer P is to 1, the more likely it's to occur. So in other words, there's more successful collisions. Single atoms have a p-value nearly 1, very high chance of reaction occurring. So single atoms have the highest chance of reaction occurring. Complex molecules have a value nearly 0, which means that there's a small chance of reaction occurring. Okay. In terms of this, before we continue, guys, this idea that single atoms have a high chance of occurring and then complex molecules have a lower chance of occurring. Well, how do these big, as an example, how do your big how do your big biochemistry or biomolecules actually react in biology? And the answer is, guys, they undergo complex mechanisms such as glycolysis, in which a very big molecule, glucose, C6H12O6, undergoes a series of chemical reactions with catalysts, okay, or enzymes, to break that molecule into smaller and smaller and smaller chunks, so it can then it will then arrive at a point in which the orientation factor is closer to 1, thus increasing the odds of a chemical reaction occurring. So in a mechanism standpoint, again, there are things in play that will take those big biochemistry molecules and slowly break them down, okay, into smaller pieces in order to increase this orientation factor. In here, though, we're not going to get into a complex mechanism like glycolysis. Instead, we're going to look at just regular mechanisms that you would see in chemistry. So with that said, which reaction would you expect to have the smallest orientation factor? Now, we have to look here. In A, we have single atoms reacting together. In B, we have diatomic molecules reacting together. And then, of course, in C, we also have diatomic molecules reacting together. So again, smallest orientation factor implies that the reaction would have a hard time occurring, versus orientation factor closer to 1 would have a high chance of it occurring. So the correct answer, guys, would be C. C exhibits the most complex diatomic molecules, as it's HCl, so you have a hydrogen and you have a chlorine, right there. So there's 2 different elements and you have 2 different HCl molecules reacting together. So that would have the the lowest chance of a chemical reaction occurring, i.e. having the smallest orientation factor. Again, HCl has to collide in a very specific manner for that reaction to occur. If it doesn't occur like that, it will not happen. So they have the smallest orientation factor out of these 3 reactions. The one that had the highest would, of course, be A. Okay? And with that being said, guys, that's the end of today's video. We'll discuss more collision theory in class. But if you have any questions, shoot me an email.